Hello and welcome to Integration by Substitution. Okay, just to start this topic, we're actually going to look at how we differentiate a function. So if you cast your mind back to Calculus 1, we have y equals sine of x squared. Well, how do we differentiate that? Hopefully you remember that's the chain rule. And we have a function of a function, and that's where the chain rule applies. If you don't recall the chain rule, here it is. So it's the derivative of f of g of x, and to differentiate that, we have f prime of g of x, so the derivative of the outside with the inside left the same, and then that's multiplied by the derivative of the inside. So hopefully that looks a little bit familiar. We take a very simple example of that. If we want to differentiate sine of x squared, we get cosine of the x squared, and then we multiply by the derivative of the x squared, so we multiply by 2x and have that on the outside. So if we know that, we hopefully also know this. If we know the derivative of sine x squared is cosine x squared multiplied by 2x, then we also know that if we take the integral, the antiderivative of cosine x squared multiplied by 2x, we get sine of x squared. We get back to where we started, with of course the plus c, the constant of integration. We know that from the fundamental theorem of calculus. So the general principle is we're going to take this function, this f of x dx, and we're going to replace it with a simpler function, hu du. We still need to integrate, we still have some work to do, but the aim is to make that integral a little bit simpler. So let's try an example and see how we can do that. Okay, here's our example, and it does look pretty ugly. We don't want to integrate that directly. I guess we could multiply out that power of 4 and multiply through, but that just sounds terrible. Okay, so we have 5, and then we have quantity x squared plus 3x plus 7 all to the power of 4, and then multiplied by 2x plus 3. And we need to pick a substitution. We need to pick a u to hopefully make this a little simpler. And if we look at this piece of the function, this is the complicated bit. It's a function of a function. So perhaps a natural choice of u is this x squared plus 3x plus 7. If you do more examples of this, the natural choice of u should hopefully become apparent. But trust me, for now, this looks like a good choice. Okay, well, let's try that substitution. Okay, that looks good. It certainly looks simpler. We have 5u to the 4. We still have that 2x plus 3 dx. And you'll notice when we talked about the principle, we really needed a function of u, and we needed a du here. Here we have a dx. So how can we do that? How can we get rid of that dx and get a du? Well, if we know that u equals x squared plus 3x plus 7, we also know that u dx is 2x plus 3. We know that derivative. And so we have this differential here that du equals 2x plus 3 dx. And isn't that convenient? That 2x plus 3 dx is exactly what we have here at the end of this integral. So we can replace that 2x plus 3 dx with a du, like so. And our integral becomes 5u to the 4 du. That looks pretty simple. Certainly much simpler to integrate for us. Now, of course, we still haven't quite finished. We still have to actually do the integration, but we can do that very easily. That's just the power rule, add 1 to the power, divide by the new power, and so sure enough, we get u to the 5. And again, the constant of integration. We've not quite finished. There's one more step we need. Because we introduced this u, we need to substitute it back in. But we know what u equals. U is that x squared plus 3x plus 7. So we can substitute that back in. And sure enough, we get x squared plus 3x plus 7 all to the power of 5 plus our constant of integration. And if you wish, you can even use the chain rule to differentiate back again to check that that's the answer. But I can show you it is. Okay, so here's our theorem. If we have f and g are differentiable functions, and we were to integrate f prime of g of x multiplied by g prime of x dx, and then our integral is f of g of x plus c. And you'll see lower down here, this is the substitution. We let u equal g of x, and then du is g prime of x dx. And that's something to look out for. We'll see that again in our second example. Okay, so again, look out here. We have sine of x cubed plus 4, and then we multiply it by an x squared. And again, if we look at this piece, the derivative of that is this piece. Essentially, we're missing a constant, but that's okay. That's easy to deal with. But if we have this thing where we have a function of a function and the inside function has its derivative outside, that's a good sign that we're going to use integration by substitution. It also tells us what the substitution should be. In this case, it's going to be u equals x cubed plus 4. Again, we need to find that differential, that du in terms of dx. And sure enough, we get this x squared as we expected. I've just rearranged slightly, so we have the x squared dx here, and that can be replaced by the 1/3 du. So replacing the x squared dx and replacing the x cubed plus 4 inside the function, we get the very simple integral of 1/3 sine u du. And again, the idea is that when we get the integral, it's very easy to do, at least certainly easier. Okay, so integrating 1/3 sine u du, we get negative 1/3 cosine u, and again with constant integration. And then we have that very last step, we have to resubstitute the u back in again. So we get negative 1/3 cosine x cubed plus 4, and then plus c. Again, that wasn't bad. We can always check if we wish by differentiating back again. Okay, so what to look out for? How do we know when to use integration by substitution? Well, if we have something of this form, again, we have this g prime on the outside and g on the inside here. If we look out for something like that, that's a pretty good sign that we're going to use integration by substitution. There are a couple of other forms you might see, and you'll see those in class and you read the book, but these are the most common we'll see. So just another example of that, we have the sine x here and the e to the cosine x. We have the function on the inside and the derivative on the outside, so that's a good sign we're going to use integration by substitution. And then finally, just something to be aware of. Often you can get to the point where maybe something doesn't cancel. Maybe you have a f of x and a g of u, functions of two different variables, and a du there. You can't integrate that. Don't try. So just an example, if I have 3x squared sine u du, don't start integrating. We still have an x left. Something has to cancel. Okay, so that is integration by substitution. As I say, you'll see more in class, but that's it for now.